So we've been talking a little bit about series and parallel circuits and identifying them and how they're configured in a circuit arrangement. What we're going to be doing here is talking about Kirchhoff's rules and how they apply. And we're going to start with series circuits. You see the two rules here. If you don't have them written down, it would be a good idea to take this moment to write them down. And we're going to be moving on here to talk about how they work in series circuits. So first we're going to address the first rule, which deals with the potential difference. So Kirchhoff's loop theorem tells us that the sum of the voltage rises, which refers to an increase in potential, equals the sum of the voltage drops, or a decrease in potential, around a closed loop. So if you picture a series circuit, and I'll draw one for you here, we have a battery. And let's say that we're dealing with resistors. So maybe we have two resistors in this circuit. So our overall circuit, series circuit, would look like this. Well, when we're talking about the loop theorem, what we're referring to is the amount of voltage that the battery has is the voltage rise, the increase in potential. As we go around the circuit, each of the resistors is part of a drop in the voltage. So if we were writing an equation for Kirchhoff's loop theorem, we would look at the voltage of the battery is equal to the voltage drop for resistor 1 plus the voltage drop for resistor 2. So we can call this resistor 1 and this is resistor 2. This would be the battery, so it would have a voltage total for the circuit. So the battery would be the rise in voltage, and across each of the resistors would be a drop in voltage. So if we had more than one or more than two resistors in series, like this, then we would be looking at an equation V1 plus V2 plus V3. So however many resistors you have, as long as they're in series, we only have one closed loop here, we would add the voltages together and the voltage drops would total the voltage gained by the battery. Often people think of a series circuit kind of like a roller coaster or a series of hills. So if you picture going around a roller coaster, we would go initially a hill. So this would be like the voltage of the battery, how you have a higher potential at the top of the battery than you do at the bottom. So this would be a high potential place, or the top of your hill, and this would be a low potential place, or the bottom of your hill. So if we continue to trace the path of conduction, the wires would be like a flat part on your roller coaster. And then eventually you come to a downhill and you lose some of the potential energy that you had gained going up the hill to start with. So on that downhill, that would be the voltage drop across resistor 1. And then that generally doesn't take you all the way to the bottom of the hill. Usually a roller coaster would have more than one downhill. So perhaps there's a little flat part again that you're going around, and then as you continue, you have another downhill at some point. But what ends up happening is that whatever you started with your voltage of the battery, that was your going uphill, you have to come back down the hill. So you're coming down through the resistor, you're coming down through the second resistor, which would be V2, and your total uphill, which is VB, equals your total downhill. So this is an analogy that sometimes helps people understand the loop rule. And this is true around any closed loop. The sum of the ups equals the sum of the downs, because you have to end right back where you started. So that was dealing with the loop rule, which relates to potential difference. And here what we're looking at is the junction theorem, which relates to the current in a circuit. Now remember, in a series circuit, or with resistors that are in series, there may not be any junctions. So if it's a simple circuit and we have just multiple resistors or bulbs in a series, there is only one loop, so there's no junction. And what a junction means is a place where there is a split in the path. So we have no splits in the path. There's only one path in this case. So if we're making an analogy to the roller coaster, this would be a roller coaster where there's only one possible track that the riders can follow. And a lot of roller coasters are like that. So think about all the people that leave the station at the roller coaster. They all have to go through every part of that ride before they can return to the station. So in this case, with a simple circuit like this, a simple series circuit, whatever current comes out of the battery is the same current that goes through 1 and 2. Let me back up there. It's the same current that goes through 1 and 2 and 3, and however many resistors are in that loop. So this would be the current through resistor 1, this would be the current through resistor 2, this would be the current through resistor 3, and they're all equal to one another. The other factor that comes into circuits besides V and I is R, resistance. And basically the total current in a circuit will always depend on the total resistance of the circuit. So a goal here is to figure out what the total resistance of a circuit is, and first we're dealing with series circuits. So let's figure out what the total resistance is for a series circuit. So the question is, what is the total resistance of resistors in series? And to answer this question, we have to think about what we just learned about the potential and the current. So first, we know that the total voltage or potential difference coming out of the battery is equal to the potential difference sum across each of the resistors. So however many resistors are in there, the total voltage equals V1 plus V2 plus V3. Now remember from earlier that V equals IR. So V total is going to equal I total times R total. V1 is going to be equal to I1 times R1. V2 is I2 times R2, and so on, for however many resistors are in that series. And what we just learned about the current is that the current is the same everywhere in series. So if every single one of the currents, IT and I1 and I2 and so on, if they're all the same, we can reduce that equation and ultimately come up with that the total resistance for series resistors is equal to the sum of the individual resistors. So this is a good amount of information here. The total voltage of the battery is equal to the sum of the individual voltages. The current is the same everywhere, and the resistance total is equal to the sum of the resistances in series circuits.